Hi guys, in this video take a look at revisiting the chain rule, reversing the chain rule for products, reversing the chain rule for quotients, examples, and then we'll finish with a summary.
So how can we use the chain rule from differentiation to integrate things? We have often used the chain rule when dealing with composite functions. For example, we integrated functions of the form f of ax plus b using the chain rule. So for example, the sine of 4x plus 1, or 2x minus 3 all cubed, or e to the power of 1 minus 1/2 x. These are all examples of composite functions, but in this case they are of a particular form, f of ax plus b. When using the chain rule for differentiation, we differentiate the outer function and multiply this by the inner function's derivative. So if we want to differentiate a composition of functions f of g of x, then by the chain rule we get f prime of g of x multiplied by the derivative of g, d by dx of g of x. Again, f is our outer function and g is our inner function. This prime symbol here refers to differentiating with respect to g of x. Normally we simplify this process by letting u equal g of x, and then our composition of functions just becomes a function of u. We differentiate u and multiply that by the derivative of the original function with respect to u, and then at the end substitute back for our functions instead of u's. In integration, we can use the same principle, but in reverse. Suppose we consider 6x multiplied by x squared plus 1 squared. We can write this as 3 multiplied by x squared plus 1 all squared, and then multiplied by 2x. Now the motivation for doing this is that then we can compare it with our chain rule above. If we consider our x squared plus 1 to be our g of x, then it is the case that 2x is indeed the derivative of g of x. And then we can choose our f of x nicely to get the pattern we want. If we look at this whole expression, we want it to be equal to f prime of g of x, the derivative of f with respect to g of x. Now again, g of x is x squared plus 1. We can essentially view this as 3u squared. And then if we let f of x be equal to x cubed, then indeed when you have f of g of x, so x squared plus 1 all cubed, and you differentiate that with respect to g of x, then you will get 3 lots of x squared plus 1 all squared. That is just seen by differentiating this with respect to x and then substituting in g of x, 3 lots of x squared, and all we do is to put that x squared plus 1 in place of x. And therefore, when we integrate this 6x multiplied by x squared plus 1 all squared, we can use the chain rule to help us perform the integration. Because we have compared it with the right hand side of the chain rule, this f of g of x is going to be our answer for the integration. Again, this uses the fact that integration and differentiation are the reverse. We are integrating a right hand side of a chain rule. And again, as always, we should not forget our plus c. Now that we have our f and g, we can write down the answer. F of x is x cubed, and g of x we're letting be x squared plus 1, and so all we have to do is to substitute x squared plus 1 in place of x, and we get x squared plus 1 all cubed, and then plus c. That is the answer to our integration in this case. We can use this approach when dealing with both products and quotients of functions. For example, we could have 2x multiplied by x squared plus 1 all cubed. This is an example of a product, and we can use this process on this. But similarly, we could have 2x divided by x squared plus 1, and we can also use this process on this, even though it is a quotient. So how can we reverse the chain rule in order to integrate products? We are sometimes required to integrate products of functions where one function is the derivative of an inside function in the product. For example, we may need to integrate functions of the form a constant multiple of some function f differentiated, and then that same function to some power n. Again, just for reference, we have k, which is some constant. We have f of x, which we're going to call our inside function. And then we have this f prime of x, which is the derivative of our inside function. And this whole expression is what we're going to call our composite power function. There are many examples of composite functions taking this form. For example, consider the function 2x multiplied by x squared plus 1 all cubed. This is similar to what we saw before. If we let f of x be equal to x squared plus 1, then indeed when we consider f prime of x, we get just 2x. And so this is the product of f of x to the power of 3 multiplied by f prime of x. So the constant n in our above expansion is 3, and the constant k is 1. There is no constant with this 2, like say a 6, which would give 12x, blah blah blah, but instead this is just 2x, as it is supposed to be. Similarly, we could have minus 2 multiplied by sine x multiplied by cos squared x. Now if we consider in particular f of x to be cos of x, this is the function being taken to some power, then we consider f prime of x, this is going to be minus sine x by our rules for how we differentiate trigonometric functions. Then in this case we have that n is equal to 2, and also we have that k is equal to 2. This is because consider the product 2 multiplied by minus sine x multiplied by cos x to the power of 2. Well, this is precisely minus 2 sine x cos squared x. We can integrate such functions using the reverse chain rule for products of functions. Suppose that we are differentiating f of x to the power of n. Then using the chain rule, this becomes n multiplied by f prime of x, and then we have the f of x again, but to the power of n minus 1. And so we can reverse this process if we integrate something of the form f prime of x multiplied by f of x to the power of n for some n. Then by doing a little bit of rearranging, this is going to be f of x to the power of n plus 1 divided by n plus 1. And then of course we have our plus c. This rule comes from the above rule with a slight bit of tweaking. All we would do is consider n being actually n plus 1 and then dividing it off, and using the fact that integration and differentiation are opposites. We can integrate things like 5 cos x multiplied by sine to the power of 4x using this reverse chain rule method for products. We consider the thing being multiplied to a high power. Therefore we let f of x be sine x. This is the thing being taken to a high power. Then we consider f prime of x just to ensure we get what we want. Well, f prime of x, lo and behold, is equal to cos x. Then if we consider just for now cos of x multiplied by sine to the power of 4 of x, then in particular it has the form that we want, which is the product of some function f differentiated multiplied by f of x to some power n. So if we integrate 5 lots of cos of x multiplied by sine to the power of 4x, then all we need to do is to have this 5 outside, and then we have our sine of x to the power of n plus 1, well that is sine to the power of 5 of x, and then we divide by that n plus 1, which is 5. And of course, as always, this is indefinite integration, and so we have our plus c. The 5's cancel out, and so we just get sine of x to the power of 5, sine to the power of 5x, and then our plus c. This is the integral of 5 cos x multiplied by sine to the power of 4x. This purely comes from the corresponding differentiation rule, mainly the chain rule, and in particular differentiating powers of functions. So how can we reverse the chain rule in order to integrate quotients? There is also a method for integrating quotients of functions where the numerator is related to the derivative of the denominator. So if instead now we have a constant multiplied by the derivative of some function x divided by that function x, then we can integrate functions of this form. Again, k here is a constant, f of x is the function we're considering, and f prime of x is the derivative of the function we're considering. There are many examples of composite functions taking this form. For example, if we consider 2x divided by x squared plus 1, if we let f of x be equal to the denominator x squared plus 1, as we have in our form above, and then we consider the derivative of this function f prime of x, we indeed get 2x, which is the numerator, and so we have that k is equal to 1. Now, if we also then consider the cot of x, this is equal to the cos of x divided by the sine of x by definition. So again, if we let our f of x be our denominator, then we have that f of x is equal to sine of x. Then we consider f prime of x, and indeed we get what we want, which is cos of x. Again, in this case, we have that k is equal to 1. We can integrate such functions using the reverse chain rule for quotients of functions. In particular, if we consider the derivative of the natural logarithm of a function, then what we get is the derivative of that function divided by the function. This result comes from the chain rule. And so, if we consider the integral of the right-hand side, i.e. the integral of f prime of x divided by f of x, then we are going to get, as expected, the natural logarithm, but of the modulus of f of x. And then, as always, we have our plus c. We can integrate 2x divided by x squared plus 1 using this quotient reverse chain rule method. So again, we have our 2x divided by our x squared plus 1, and so we're going to let our function f of x be the denominator, which is x squared plus 1. And then we check, and indeed when we differentiate this function and get f prime of x, we do indeed get the numerator 2x. And so 2x divided by x squared plus 1 does indeed have the required form, which is f prime of x divided by f of x for some function which we have identified f of x. And so therefore, if we consider integrating this function 2x divided by x squared plus 1, we're going to get the natural logarithm of the modulus of f of x. And so it's the modulus of x squared plus 1. And then, as always, we get plus c. And then, because we have that x squared plus 1 is certainly a positive number, since x squared itself is greater than or equal to 0, and so when you add 1, you certainly get strictly greater than 0. And therefore we can remove our modulus signs, and we get the natural logarithm of x squared plus 1 without any modulus signs. And as always, we have our plus c. Let's take a look at some examples. Our first example asks us to use the reverse chain rule method to find the indefinite integral 6x multiplied by e to the power of 3x squared. Our first step is to recall the reverse chain rule for products. We have that if you want to integrate a function of the form f prime of x multiplied by f of x to the power of n for some value of n, then the result is f of x to the power of n plus 1 divided by n plus 1. And as always, we have our plus c. You can sort of see how this compares to when we have our rule for integrating ax to the power of n. It's just the case that we set up this left-hand side so nicely that we get this rule. Our second step is to identify the inner function and find its derivative. If we consider the derivative of e to the power of 3x squared, then by using the chain rule, we get the derivative of 3x squared multiplied by e to the power of 3x squared. Since e to the power of x in general differentiates to itself, all we need is the derivative of the inside. And so we get 6x by the derivative of 3x squared multiplied by e to the power of 3x squared. So if we let our function f of x be e to the power of 3x squared, then this means that we have our derivative of our function f prime of x being equal to 6x multiplied by e to the power of 3x squared. Now, after obtaining this result, you may see how to get the answer immediately, but I'm going to go through the process in full generality in order to show how the process goes. Now, this means that 6x multiplied by e to the power of 3x squared is in fact equal to f prime of x, just by reversing the above inequality. But in particular, it's equal to f prime of x multiplied by f of x to the power of 0, since that is 1. The reason I do that is to put it into the exact required form that we need in order to integrate it. Our third step is to integrate the expression. So now if we want to integrate 6x multiplied by e to the power of 3x squared, then this is the same as integrating by our definition of f prime of x multiplied by f of x to the power of 0. And therefore, based on our integration rule we had above, we're going to get f of x to the power of 0 plus 1 divided by 0 plus 1 plus c. And so we get just that. F of x to the power of our value of n, 0, and then we add 1, and then we divide by 0 plus 1, and then of course, as always, we have our plus c. Our last step is to write down the simplified integral, remembering to add a constant of integration. All that remains is to simplify our values of 0 plus 1 and 0 plus 1, and to substitute in the value of f of x. And so we get, for our integral of 6x multiplied by e to the power of 3x squared, f of x to the power of 1 divided by 1 plus c, which is just f of x. Now f of x is e to the power of 3x squared, so we get e to the power of 3x squared and then plus c. Now I was mentioning earlier that you may have already spotted how to get the answer almost straight away. When we considered this derivative, we got the answer we needed, and so the answer is going to be e to the power of 3x squared plus c all along. But for full generality, I showed you the whole method. Our last example says using the quotient reverse chain rule and the fact that tan x is equal to sin x divided by cos x, show that the integral of tan x is the natural logarithm of the modulus of sec of x plus c. Our first step is to recall the reverse chain rule for quotients. When we integrate f prime of x divided by f of x, we get, by using our reverse chain rule for quotients, the natural logarithm of the modulus of f of x. And of course, as always, we have our plus c. Our second step is to identify the inner function in the denominator and its derivative in the numerator. We were told in the question to treat tan of x as sin of x over cos of x in order to get a quotient. So if we consider our denominator and we differentiate it, so if we differentiate cos of x, then we end up with minus sin of x. So therefore, if we let our f of x be equal to cos of x, then we get that the derivative f prime of x that we just found is equal to minus sin of x. Then if we consider tan of x, which we're looking to integrate, then this is going to be equal to minus f prime of x. This gives us just sin x on the numerator. Again, just for extra clarification, we have this minus sign on the top in order to definitely get a sin x rather than a minus sin x, which is what f prime of x is ordinarily. And then we have division by f of x. Just to carefully identify everything with the f's, minus f prime of x is equal to sin x by the above expression, and by definition, f of x is equal to cos of x. So we can definitely see that tan of x is equal to this quotient minus f prime of x divided by f of x, by definition of tan of x as sine of x divided by cos of x. Our third step is to integrate the expression using this above knowledge. Again, we have found that tan of x, which is written as sine of x divided by cos of x, this is the definition of tan of x in general, is equal to minus the value of f prime of x divided by f of x. And so, if you want to integrate tan of x, it's the same as integrating this minus f prime of x divided by f of x, by the definition of f of x. And so, by our integration rule for the reverse chain rule dealing with quotients, we get the minus, using the minus here, of the natural logarithm of the modulus of f of x. And of course, as always, our plus c. Our fourth and final step is to write down and simplify the integral, remembering to add a constant of integration. So, we get the integral of tan of x, which we're hoping to evaluate, is equal to, just by substituting in our f of x, minus the natural logarithm of the modulus, and our definition of f of x was cos of x. So we get a cos of x inside this modulus, and then we have our plus c. So the final thing to do is to use our logarithm rules and our definition of sec of x. We get this is the same as the natural logarithm of 1 divided by the modulus of cos of x. This is bringing the minus 1 inside. And of course we have our plus c. Now we can distribute the modulus just for effect, so we get the natural logarithm of the modulus of 1 divided by cos of x. Now the reason why I do this is because now I can very carefully substitute in our definition of sec of x, and so we get the natural logarithm of the modulus of sec of x plus c. The only possibly confusing step was why I did this step to this step, and I was doing it to be very, very careful about our substitution of sec x as 1 over cos x. If you're particularly fluent, you can go straight from this step to this step.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face, and together, let's make A-level maths a walk in the park.